Hello friends, welcome to the today's lecture. And if you remember, in previous lecture we have discussed this, that if we have a functional defined as this I of y of x is equal to a to b f of x y y dash d of x here, and if y of x is a curve on which this functional achieve an either maxima or minima, or you can say that on this curve y of x this curve achieve the extremum, then the Euler's equation we have derived in last lecture, that is dou f by dou y minus d by d of x f of y dash is equal to 0. So it means that if y of x is an extremal of this, then it must satisfy this Euler equation. And if you simplify this, it is nothing but dou f by dou y minus, here I can assume this as f of x y dash minus f of y y dash minus f of y dash and y double dash. So here I am assuming that f of y dash is a function of x, then we write with respect to we differentiate with respect to x. Here we assume that f of y dash is a function of y, so we differentiated with respect to y and y dash. Here we take the part of f of y dash as depending on y dash, so f of y dash y double dash is equal to 0. So it means that if y of x is extremal, it must satisfy this differential equation, which is a second order differential equation in the variable y, and we want to find out say solution. Here please note down that this y of x is a solution extremal of this, provided that y of a equal to 0, y of a equal to y1 we have assumed, and y of b equal to y2 we have assumed. So this is already given. So it means that to find out extremal, we need to find out the solution of the second order differential equation satisfying the boundary condition. So in general, this is not always having a solution. So here we may remark that we may recall that the boundary value problem fy minus d by dx f of y dash equal to 0, satisfying the boundary condition, that is y of a equal to y1 and y of b equal to y2, does not always have a solution, and if the solution exists, it may not be unique at all. So let us take one example and try to see whether this remark is how much it is true. So for that, let us take the extremal of the function I of yx equal to 0 to 1 xy plus y square minus 2y square y dash d of x, with the boundary condition that y of 0 is equal to 1 and y of 1 is equal to 2. So these boundary conditions are already listed in the given problem. So let us take this particular example, 0 to 1 xy plus y square minus 2y square y dash d of x, y of 0 equal to 1 and y1 equal to 2. So we have written down the functional x, this I of y of x is equal to 0 to 1 xy plus y square minus 2y square y dash d of x, with the boundary condition that y of 0 is equal to 1 and y of 1 equal to 2. So here from this it is clear that f of x, y and y dash is equal to xy plus y square minus 2y square y of dash. So to find out the differential equation which a extremal function satisfy, we recall the Euler's equation, that is f of y minus d by d of x f of y dash is equal to 0, which gives us differentiation with respect to y, it is x plus 2y minus 4y y dash minus d by dx of fy dash. So d by dx of fy dash will be, it is minus 2 of y square. So, which is nothing but is equal to 0. This simplify x plus 2y minus 4y y dash minus, if you write it here, then it will be this plus sign 4 y and y dash equal to 0. So, these two will cancel out and you will have that x plus 2y has to be 0. So, this implies that y has to be minus x by 2. So, it means that if we have an extremal of this functional, then that extremal function y of x must satisfy this Euler's equation, or we can say that your extremal function must be of this form, that y of x is equal to minus x by 2. Now, if you look at the boundary condition, then y of 0 equal to 0, and here if you look at the value of y of 0 is coming out to be 0. So, it is not no, y of 0 is equal to 0, but if you look at the boundary condition is y of 0 is equal to 1. So, it means that the functional which satisfy the Euler equation is not satisfying the boundary condition given with the functional. So, it means that this y of x equal to minus x by 2, though it satisfy the Euler's equation, but it is not a solution of the boundary value problem. It means y of 0 equal to 1 is not satisfied in this particular case. So, here we say that this functional does not have any extremal, right, because it is not the solution of boundary value problem. It may be a solution of only equation, but not satisfying the boundary condition. So, in this case we say that this functional does not have any extremal. Okay. Now, moving on to the next cases, let us consider the case 1. Here we are considering the case depending on the form of f. So, here since f involved x, y and y dash, so here we are considering the case that f is written only in terms of x, y, in terms of y dash, in terms of y, all these cases we want to consider, and we try to see that the simplified version of Euler's equation. This is just a sub cases of this Euler's equation. So, first let us consider the case 1, when f is equal to f of x y, it means that f is independent of y dash. So, if we take f as independent of y dash, it means that double f by double y dash is equal to 0. In this case, your equation, Euler's equation, which is given by double f by double y minus d by dx of f y dash. Now, f y dash is equal to 0. So, second term of Euler equation will be 0. So, it will reduce only in the first term, that is double f by double y equal to 0. And if you solve this, if you integrate with respect to y, you will say that you will get certain function f. Now, here this f y x y equal to 0, the solution of this finite equation does not contain any arbitrary element, therefore. Why? Because double f by double y equal to 0 means that f is constant with respect to your variable y, and it is already given that f is independent of y dash. So, it means that this f is basically independent of both say y and y dash, and here it may happen in general that it does not satisfy the boundary condition. So, hence there may not exist any solution of this variation problem also. It may happen a solution exists only in the condition that the this solution of this finite equation, that is f y x y comma equal to 0, pass through the boundary points. So, in that case only we may have a solution, otherwise it may not have a solution. So, let us move to one example based on this and try to see what we are trying to explain here. So, let us first let us look at here the extremize of L of I of y of x equal to 0 to 1 x sin y plus cos of y d of x with the boundary condition y of 0 equal to 0 and y of 1 equal to pi by 2. So, here if you look at the f of x y y dash is given as x sin y plus cos of y. So, here f of x comma y dash is equal to x sin y plus cos of y. So, it is independent of y dash. So by Euler's equation, if you simplify, this term is simply vanished. So we will have del f by del y is equal to 0. So calculating del f by del y, it is nothing but x cos of y minus sin of y is equal to 0. So if you simplify, it is coming out to be that y of x is equal to tan inverse x. Now so we are able to find out the solution of Euler's equation. Now coming on to the boundary condition. So boundary condition is y of 0 equal to 0 and y1 equal to pi by 2. So if you take that x equal to 0, then tan inverse 0 is 0, but if you take x equal to 1, then tan inverse 1 is equal to pi by 4. So here this solution does not satisfy the second boundary condition, that is y1 is equal to pi by 2. So here for this particular problem we do not have any solution, or we can say that y of x equal to tan inverse x is not a solution of this, is not going to extremize the functional with the boundary condition this. But if you look at here, if we have y1 equal to pi by 2 is replaced by say pi by 4. So in that case the extremal y of x equal to tan inverse x pass through the boundary points, means 0 0 and 1 pi by 4. So in that case, when the functional comes with the boundary condition defined at 1 as pi by 4, in that case we can say we have a solution, otherwise in this particular case we do not have any solution. So in the case when f of x comma y dash is independent of y dash, in that case in general there may not be a solution. Now moving on to the second case, here we are assuming that f is a linear function in terms of y dash. So or we can write that f is equal to m of xy plus y dash n of xy. So in previous case we have seen that n of xy is coming out to be 0 only. So here we say that we are it may happen that f is not say independent of y dash, but it is a linearly dependent on y of dash. So in this case if you find out say Euler's equation, then calculating del f by del y, which is nothing but del m by del y plus and y dash del n by del y. Okay. So and del f by del y dash is calculated as n of xy. So if we look at the Euler's equation, then Euler equation is what? Del f by del y minus d dx of del f by del y dash. So we can say that del f by del y is this del m by del y plus y dash del n by del y minus d dx of nxy. So d dx of nxy will be del n by del x plus y dash del n by del y is equal to 0. Now if you simplify this term, and this term will be cancelled out. So this term and this term will be cancelled out, and it is reduces to del m by del y minus del n by del x is equal to 0. So it means that del m by del y is equal to del n by del x is the form of the Euler's equation. Here we have seen that if Euler equation gives us that the condition del m by del y equal to del n by del x, and we can say that this is not a differential equation, rather than it is a finite equation. Now it may happen that this curve which we have achieved as an application of Euler's equation may not satisfy the boundary condition, and if it is not satisfying the boundary condition, we simply say that the variational problem does not have any solution in the class of continuous function. But if this del m by del y is unequal to del n by del x, or you can say that this my minus nx is unequal to 0, then the expression the Euler equation is ideally satisfied, and in this case this expression m dx plus n dy is an exact differential, and we can write it I as x naught to x m plus n dy by dx, and it is nothing but x naught to x1 m dx plus n dy. And we already know from the theory of ordinary differential equation that m dx plus n dy is an exact provided my minus nx is equal to 0. So in that case it is an exact derivative of some function, and we can say that the value of I is given as the value at the endpoints, and in that case whatever path you will choose, your value of I is coming out to be a constant value, and in that case your variational problem become meaningless. Let us try to understand the theory. Let us understand more about this theory by taking a particular example. So let us take this example. Here we take a functional I of y of x is equal to 0 to 1 y square plus y dash x square d of x with the boundary condition that y of 0 equal to 0 and y of 1 equal to a. So here f can be written as y square plus y dash x square. Now if you look at it, contain all the term x, y, y dash, but if you look closely, then you can say that f is linearly dependent on y of dash. So if you write down the Euler's equation, Euler equation is f of y. So f of y is 2y minus d by dx of f of y dash, which is nothing but x square. So we can simplify and you can write it that the solution of this Euler equation is nothing but y equal to x. So it is not a differential equation, but it is just a finite equation. Now let us look at the boundary condition now. So if you look at the boundary condition, y of 0 is satisfied, but if you look at the second condition, that is y of 1 equal to 1 here, which is not matching with the given boundary condition, that is a. So if a equal to 1, we can say that y equal to x is a extremal of this functional. In fact, this is going to be a minimal curve for this functional. But if a is not equal to 1, we can say that we do not have any extremal for in this case. So we can say in case of a equal to 1, y equal to x, basically minimize this this functional. But if a is not equal to 1, we say that we do not have any extremal at all. Now let us consider the other example for which this Euler equation gives you an identity. So let me write it here. So here we want to consider the case when my is ideally equal to n of x. So let us consider a function like this, I of y of x a equal to x naught to say x naught to x1, x naught to x1. Let us take the simple example, say y plus y dash x d of x. Okay. So this is the simple example. Now in this case, your f of x y y dash is given as y plus y dash x y dash into x. So here if you find out, say Euler equation is fy minus d by dx of fy dash, which is equal to 0. So this implies that f of y is simply 1 minus d by dx of y dash, that is simply x. So d by dx of x equal to 0, and if you look at this is nothing but 1 minus 1 is equal to 0. So here in this case we have an we can say that your my is ideally equal to n of x. So in this case, if you look at, this is what? This is nothing but d of x of y with respect d of xy, so with respect to d of x. So in this case your I of y of x is nothing but x naught to x1 and y plus y dash x d of x is written as x naught to x1 d of xy, and it is nothing but xy evaluated at x naught to x1. So this is and here please remember, here the condition is also given that let us say y of x naught is equal to y naught and y of x1 is equal to y1. So using this boundary condition, this can be written as say x1 y1 minus x naught y naught. So it means that this is a just a constant value. Now here please remember that here if we can take any curve which satisfy this condition y of x naught equal to y naught and y of x1 equal to y1, and if you take any curve, your value of the functional is coming out to be this constant value, that is x1 y1 minus x naught y naught. So here the value of I of y of x is fixed and it is equal to this. So here the quotient of say extremizing the function is now meaningless, because this integral is independent of the path between joining these 2 points x0 y0 and x1 and y1. So it means that this is the point x0 y0 and there is a point x1 y1. You can take any path, whether you take this path, that path, or whatever path, the value of this I of yx is nothing but the value given here, that is x1 y1 minus x0 y0. So it means that every curve is extremal. So we can say the problem of extremal is meaningless here. Now going into the third case, here we are assuming that f is depending only on y of dash. So in this case your Euler's equation, f of y minus f of x y dash minus y dash f of y y dash minus y double dash f of y dash equal to 0 reduces to, because here f is depending only on y dash, so it is independent of y, independent of x. So here we can write that this will reduce to only this term, that y double dash f y dash is equal to 0. So either this term will be 0 or this term will be 0. So if y double dash is equal to 0, we can solve this differential equation, then we can get y equal to c1x plus c2x, and it is a 2 parameter family of straight lines. But if we look at this f of y dash which is a function of y dash is equal to 0, we can solve this and we can find out the root, and that root is in terms of y dash. So if we take the roots of this equation y dash equal to cj, we can solve and we can get that y equal to cix plus c as a solution. So in this case the extremals are all possible straight lines. So let us take one example based on this, and the example is quite interesting. The example is basically finding the curve of least length joining 2 points in a plane. So we have a plane, xy plane, and we want to find out, say, the minimum curve of minimum length. So let me write here. So problem is this, that we have a 2 points, say x0 y0, and we have one more point x1 y1, call this point as A and this point as B, and we want to connect these 2 points by several say curves, curves you can say find out joining these 2 points A and B. What we want to define is the function like this, which says that between x0 to x1 we have, say, for every curve we have a length of the curve, and we want to find out the curve which minimizes the length of the curve. So here you can say that d of s is the say this length element, and we can write it this as x0 to x1, this is nothing but 1 plus dy by d of x whole square and d of x. So we can say that in this case your functional is the functional is to minimize or maximize the length of the curve joining the point x0 and x1. So here the condition is given that y of x0 is equal to y0 and y at x1 is equal to y1. So what we want to find here, we want to extremize the function given here. So in this case your f of xy y dash is nothing but your under root 1 plus y dash square. So this is totally depending on only y dash, no term x and y is present here. So this is the case lying in your this case 3, where f is independent of x and y, it is totally depending on y of dash. So here this is the functional which we have just defined, I of y of x equal to x0 to x1 under root 1 plus y dash square d of x, and we want to find out the curve which extremizes this functional. So here f is equal to under root 1 plus y dash square, so del f by del y is equal to 0, and you can say del f by del y dash, you can calculate it is nothing but y dash upon under root 1 plus y dash square. So Euler equation is reduced to this, that d by dx of y dash upon under root 1 plus y dash square is equal to 0. So we can integrate with respect to x, and we can say that y dash divided by under root 1 plus y dash square is equal to c1, and we can simplify and you can get that your y dash is nothing but c1 upon 1 minus c1 square, and which is nothing but another constant which we can call this as c. So y dash is coming out to be c, and if we integrate this with respect to x, we can get y equal to cx plus d, and if you look at this is nothing but a straight line. So it means that the straight line is the curve which minimizes the functional, so it which extremizes this functional. So in this particular case, we can say that the shortest curve joining these 2 points A and B is the straight line. So here we wanted to prove and that we already know that the a curve having the shortest length joining any 2 point is nothing but a straight line, and with the help of this case we are able to prove that it is coming out to be the a straight line only. So in this case your solution is coming out to be y of cx plus d, and if you want to find out what is the value of c and d, you can use the boundary condition, and you can say that at x equal to x1 it is y1, so y1 equal to cx1 plus d, and y0 is equal to when x is equal to x0. So you can say that you subtract and you can get c as say y1 minus y0 divided by x1 minus x0, which simply say that c is the slope of a straight line joining these 2 points x0 y0 and x1 y1. Similarly, once we know this c, you can find out d from any of these two equations. So you can find out d. So it means that in this case the straight line is the curve at which this functional I of y of x is extremized. So in this particular case, this extremal curve is the curve of minimum. So we can say that at a straight line minimizes the length of the curve joining these 2 points x0 y0 and x1 y1. Okay. So now moving on to the next case. The next case is that f of x y dash, and that f is written as f of x comma y dash, so it is independent of y here. So if it is independent of y dash, then the first term of the Euler's equation del f by del y is simply 0, and in this case your Euler's equation reduced to d by dx of del f by del y dash is equal to 0. We can integrate with respect to x, and we can have your del f by del y dash is equal to constant. Now here we can solve this equation which does not contain y either directly for y dash, or you can use some kind of parameter to solve this. So let us take one example to have more understanding of this. So let us take this example, and it is the basically functional which consider the time taken by a particle moving from one point to another point. So it is what, find the curve that on which the time taken along which is the least when velocity at any point of it is v equal to x. So basically what we are trying to do here, this I of y of x is actually calculating say time, because if you look at here in a right hand side, this under root 1 plus y dash square d of x is nothing but d of s. So we can say that it is I of y of x is equal to x0 to x1 ds by velocity. So ds by velocity is nothing but time calculated from x0 to x1. So it means that this function is nothing but time taken along which your particle is moving with the velocity v equal to x. So here if you look at f is nothing but f of x comma y dash, it is independent of y here. So here in this case you can solve this, and you can have Euler equation, which simplify here as y dash upon x plus under root 1 plus y dash square is equal to constant. So let us take this constant as C1 dash. Now here we have different ways to solve this. One way is to take this y dash is equal to some kind of parameter. Another way is to take simplify this for y dash and then try to solve. So let us let me solve this by taking the some parametric representation of this y dash. So here we can take dy by dx equal to tan of t. If we take dy by dx equal to tan of t, where t is some kind of parameter, then equation 11 reduces to this, y dash is tan of t and under root 1 plus y dash square is reduced to sec of t. So you can find out the value of x, which is nothing but C1 psi t, where C1 is nothing but the reciprocal of this C1 dash. So here x can be written as C1 t. Using the value of x, you can simplify dy by dt. You can calculate the value of dy by dt, that is this is equal to dy by dx and dx by dt. So dx by dt is already known to us, that is derivative of this x, that is C1 sin t, and so you can find out dy by dt equal to dy by dx, that is tan t, dx by dt is C1 cos t. If you simplify, it is coming out to be C1 sin t. So you can find out say y in terms of t by solving this first order differential equation. So when we solve this, it is coming out to be y equal to C1 cos t plus C2. Now here again I am using this C1 as minus of C1. So here I can say that this is the solution of the Euler equation. So here given in a parametric form. So here we can simplify and we can write y minus C2 equal to minus C1 cos t, and if we write it here, then we can eliminate the parameter here. So y minus C2 is equal to minus C1 cos t and x is equal to C1 sin t. So we can simplify this and we can remove the parameter t, and we can say check that this is nothing but the solution of this x square plus y minus C2 whole square equal to C1 square, which is nothing but the equation of family of circles here. So it means that here in this case the curve on which the time taking is the least, and when the velocity is given as v equal to x. Let me solve this equation number 11 directly by direct method. So here we have already seen when we take dy by dx is equal to tan t, then we already know that we can solve this in terms of parameter. In this case your x equal to C1 t and y is also given as C1 cos t plus C2. Now let us take this problem given in equation number 11 and try to solve without taking the help of parameter. So here we have seen that this equation number 13 we have solved with the help of taking a parameter value for y dash, but we can also solve in a different way, or we can say direct way. So here let us take this constant as say there we have taken it is as C1 dash, so we can take C1 dash here. So here we can square it and we can say y dash square is equal to C1 dash square x square 1 plus y dash square, and if you simplify you can take y dash square as 1 minus C1 dash square x square equal to C1 dash square x square here. So y dash square is equal to C1 dash square x square upon 1 minus C1 dash square x square, and you can write it y dash is equal to C1 dash x upon under root 1 minus C1 dash x square. So you can solve this by so here y dash is equal to this, and we can solve this by writing dy by dx is equal to say C1 dash x upon under root 1 minus C1 dash x square, and this you can solve by simple integration, and you can check that here we are getting the similar kind of a solution here. Okay, that is the solution is similar to the family x square plus y minus C2 whole square plus C1 square. So here you may get a different constant for integration. So here you can write it that y is equal to integration, you can write it C1 dash x upon under root 1 minus C1 dash. I think this is square here, this is square here, this is square here, C1 dash square x square d of x plus some kind of C2 here. So you can simplify by writing 1 minus C1 dash square x square as t. So let me write is 1 minus C1 dash square x square as say t square. So you can write it minus 2 C1 dash square x d of x equal to 2t dt. So 2 will be cancelled out and you can simplify, that is y equal to, so you can say that minus C1 dash is coming inside, so you can write it 1 upon C1 dash is equal to, this is nothing but t of dt, and this denominator is also written as t here, plus C2, and the here your constant will be this integration with respect to x0 to x1. So the corresponding value of t you can calculate. So t is nothing but under root 1 minus C1 dash square x0 square. Similarly here we have 1 minus C1 dash square x1 dash square, right. So you can say that this is nothing but y equal to 1 upon C1 dash, and here you will get there is a 1 minus sign also because of this. So here it is. So here I can write it here as 1 minus C1 dash square x0 square minus under root 1 minus C1 dash square x1 square and plus C2. So here you can say that your solution is also of this type, or you can say that y minus C2. So if I take say x1 as variable thing, then it is nothing but y minus C2 is equal to 1 upon C1 dash under root 1 minus C1 dash square x0 square minus under root 1 minus C1 dash square x1 square. So it is also of the previous type. If we assume that x1 is a variable point x, then you can say that this is nothing but a family of circle. You can square it and you can say that it is also a family of circle. So here we have seen certain cases of Euler's equation when f of x, y and y dash is assuming a very say particular cases, and there is one more case left, that is the function f of x, y, y dash is independent of x. That is quite important, but we will discuss in next class. So today what we have discussed, we have seen the particular example based on Euler's equation, and we say that how to find out say extremal of a given functional. So we will continue this in a next class. Thank you very much for listening us. We will meet in next class. Thank you.